Canadian Space Agency. So I'm René Doyon, I'm professor at the Physics Department of the University of Montreal, and I will introduce David tonight. But before I do that, let me give you the context of this special lecture. So this week, we have this incredible conference entitled Exploring the Universe with JDubs T. It is hosted at the University of Montreal. So there's about 150 people all over the world coming here to discuss and exchange ideas of the great things we're going to do with this powerful telescope that will be launched in 2018. So JDubs T certainly qualifies as one of the most complex machines under construction by humanity. This is an $8 billion project led by NASA in collaboration with the European Space Agency and Canada, the Canadian Space Agency. So David Charbonneau is one of our invited speakers for this conference to discuss a very important science topic, exoplanets, so planets that orbit other stars. David's research focuses on the discovery and characterizations of exoplanets with the ultimate goal of identifying inhabited worlds. He was the first to observe a planet eclipse its parent star. This method, known as transits, is now the means by which most planets outside the solar system have been identified. He also developed the first methods which astronomers use to study the atmospheres of these distant worlds. He currently directs the mirth project, which aims to find the first habitable exoplanet.
But on a clear sky night, of course, it's stars all the way down. So you all know that we are only one of 300 billion stars in the galaxy, a lot of potential abodes for planets and for life. Are we the first generation to ask this question? No. If I look back through the written record, I see humans wondering whether or not we are alone for as long as we've been putting our thoughts down in writing. Okay, so here is some thoughts on that topic from more than 2,000 years ago from the Greek Epicurus, writing to a friend. And he wrote, "There is an infinite number of worlds, some like this world and others unlike it. Some of these worlds contain the seeds out of which animals and plants arise, and all the rest of the things that we see." So even though the Greeks didn't have an understanding that the points of light in the night sky were stars and that there might be planets around that stars, they had this idea that there were other worlds and that somehow we could come into contact with those other worlds. Then if we zoom ahead, but still look back almost 500 years, here is another thinker, Giordano Bruno. And here's what he wrote. He said, "There are countless suns and countless Earths, all rotating around their suns in exactly the same way as the planets of our system. The countless worlds are no worse and no less inhabited than our Earth." Okay, so by this point in human history, we had figured out that points of light in the night sky were stars. Giordano didn't know that there were planets around those stars, but he thought there might be, and surely there might be life on some of those planets. My point is that humans have been thinking about this for a long time. We are very privileged to be alive at the moment in human history where we might have the technological ability to go and actually answer this question. So we don't have to just think about it. So how are we going to do that? What would it take? Okay, so there have been different ideas proposed. Maybe this is the way to go. Does this look familiar to any of you? Yes, the movie Interstellar, very good. I'm a big fan of science fiction. Maybe we should build spaceships, right? We should actually travel to the closest stars, land on the surfaces of planets, or at least take pictures. I'm sad to report that this is not going to be the way that I think, are going to first make those discoveries. I do think we need to build the infrastructure to actually travel beyond the solar system. I think that's incredibly exciting, but that is generations away. There's an enormous investment to get us out into deep space. I can't wait that long. So I don't think spaceships are the way to go. Okay, so other thoughts about how we might do it. Here's another one. Right? Listen, right? SETI, the search for extraterrestrial intelligence. Maybe what we should do is hope that there are other civilizations out there that build radio telescopes and have public astronomy nights. They want to communicate, so they beam messages to us. Well, the unfortunate news is that we've been listening now for more than 40 years, and we haven't heard anything. Now, maybe we've been pointing at the wrong stars or listening to the wrong frequency. And there are people who continue to advocate for SETI, and again, I'm really glad that some folks are doing it. But the more I push on this idea, it looks to me like we're looking for copies of ourselves, right? Down to the details of the kinds of telescopes and technology and the desire to communicate. Maybe that's a very human trait, not necessarily a global trait of life. So I don't think that listening is the way to go. What I do think is the way to go are telescopes. So a telescope for me is my spaceship, right? A telescope allows me to, in a sense, travel to a distant planet to see what the surface conditions are like, to explore that planet as I come up with different questions, and to travel from one planet to the next by pointing my telescope in different directions. Okay? So for me, a telescope is a spaceship that I can actually build in my lifetime. So what has the challenge been for humanity? Why has progress been so slow? Why did that Greek fella and Giordano, why did they not get to answer this question? Okay, so I want to set the scale of the challenge. So this is everything you know and love, right? There's the Earth, sum total of human thought, all of our art, all of our poetry, all of our aspirations for the future, everything on this blue marble. It looms awfully large in our minds, doesn't it? Well, let's put it in context. So I'm gonna compare it to another planet in the solar system, Jupiter. Okay, so drawn to scale, you must remember that the Earth is tiny compared to Jupiter. The Earth is only about 1/10 the size of Jupiter. So the Earth is not very important from a perspective of the solar system. Well, let's put Jupiter in context. So now I'd like to compare Jupiter to the Sun. All right, so let's bring the Sun up. There it is. So everything drawn to scale, Jupiter is small compared to the Sun, and the Earth you can't even really make out on the slide anymore. So the point is, the reason humans had to wait so long to learn about planets orbiting other stars is that planets are really small and dim compared to their central stars. So when we point a telescope at a nearby star like the Sun, the glare of that star overwhelms any potential light from the planet. And so it was only recently, only in our generation, that we have figured out how to overcome that barrier. So what is the clever idea that we're going to base our investigation on? Well, I already showed it to you. Right, that's the title slide. And so if you look at the end of the title, that's not a period. This is an actual image. Let me just get rid of the words. That's an actual image of the Sun. That's an image of the Sun taken at a very special moment in 2012. Did anybody see this? If you saw this, put your hand up. All right, so you all know that is the planet Venus. Okay, so that's not photoshopped. That's an actual picture of Venus when it was in front of the Sun. That transit of Venus, that idea of a transit allowing you to learn about a planet when it passes in front and is backlit by its star, is the clever notion that we're going to employ in our talk today. Now, people have been thinking about transits of Venus for several hundred years. And if I zoom in on Venus, so I'm going to zoom in on Venus and see what I can see. And I'm going to just bring down these lights a little bit. Okay. All right. So, you see it? So there was a Russian scientist by the name of Lomonosov, who in the 1760s was observing transits of Venus. And here's Venus, right? So that's Venus in front of the Sun. The Sun at this scale would go down several stories here. But he noticed something really interesting. He noticed that before Venus was entirely upon the disk of the Sun, he could still make out the outer limb of Venus. Okay, so he saw this glowing ring, even though Venus wasn't yet in front of the Sun. And he said, oh, I know what that is. That's refraction. That's the bending of light due to a gas. Therefore, Venus has an atmosphere, just like the Earth has an atmosphere. And it was a remarkable inference. Of course, he was correct. And it is the exact same idea that we're going to employ to actually go and try to learn about the atmospheres of planets orbiting other stars. Okay, let's bring this up slightly here. Good. Okay, so what's the plan? Plan for today. So the plan for today is the following. There's three things I want to do. I want to describe the methods by which we actually find planets and characterize their properties, and then I want to bring you up to speed on our current state of knowledge. So it's been a really exciting, I don't even want to say it's been an exciting decade. It's really been an exciting 18 months. It's really just in the last, can you believe that? It's in the last 18 months that we have actually figured out how common Earth-like planets are in the galaxy. We've begun to discover them and even think about characterizing them. And that's just happening now. We're really at this special time in human history. And then I want to present this kind of first opportunity for going and detecting life on an exoplanet. Okay, so what are the methods? So the methods, there's two methods that you need to understand before we go ahead. The first is the Doppler method. So the basic idea is the planet and the star go around each other. Here you're seeing the star, but you don't quite see the planet. So we might sometimes think of the star as being fixed and the planets go around the star, but actually the planets and the star orbit around a common center of mass. So think of it as like a dance, but the dance partners differ in weight by like a factor of 1,000. Okay, so you see this one really big dance partner, but you kind of see that they seem to be spinning with something else. So if you can see the light from the big dance partner, and you can measure the Doppler shift, the change in the frequency of light as the star goes in its orbit, then you can say, there must be something else there, and I can calculate the mass of that thing. And that's the essence of the Doppler method. The other method is, of course, the one I've already introduced, the transit method. So the idea is the planet, just if we happen to be aligned, it's only a fraction of the systems, we see if our line of sight is aligned with the orbit of the planet goes in front of the star, and it blocks some of the light. Unlike the case of Venus, we don't actually see the black dot because we don't resolve the surface of the star, but we can measure the brightness of the star, and as we measure the brightness, we can see it gets fainter for a period of time and then brightens up again. And so the idea is if we put those together, and you have a sphere, and you can measure the mass of the sphere, and you can measure the volume of the sphere, then you can calculate the density of the sphere. And so we can then begin to place these planets in context. We can figure out how big they are, and maybe even what they're made of by inference of their density. So small planets that have high density similar to rock might be rocky Earth-like planets. Okay, so that's the basic approach. All right, so transits are special because they allow us to study planets that we can't see. So all of the planets I'm going to discuss, I've never seen them directly, I've never taken their picture, and I probably never will. But I know more about them than planets for which I even could take their picture, because these methods are so penetrating. So this idea has really taken off. So as a graduate student, I was very fortunate to be the first person to measure this, to see an exoplanet transit. And that was in 2001. We knew of one such planet. Then here we are in 2016, and now there are roughly 4,000 such exoplanets. So not just 4,000 planets, 4,000 transiting planets that we know about, and then we can do an enormous amount of comparative statistics and really put the solar system in context. Okay, so the other thing that transits do is, in addition to actually discovering the planets and measuring their densities, when they go in front of the star, we turn the star from being a foe, something that prevents us from looking at the planet, to being an ally. We use the star's light to probe the planet atmosphere, right? So the light from the star passes through the planet atmosphere and then travels to our telescope, and we record that light, and we see the appearance of signatures that are due to whatever atoms or molecules are interacting with that starlight as it passes through the planet's atmosphere. So we can infer the presence of water or methane or carbon monoxide, whatever the planetary conditions are encoded in the starlight. So if we then begin to think about life, are there gases that life makes that we could then study remotely? So that's the connection. So of course there are, right? Here we have evidence of life on the Earth. And what does that life do? It photosynthesizes, right? So it takes the light from the star, and as a byproduct, it makes oxygen. So what if using this idea of transits, I can not only discover planets, I can study their atmospheres, but I can look for the chemical byproducts of life. So there's no desire of life. It's not like SETI. There's no desire to communicate. Life is going about its business, and we are literally going about its business, and we are detecting the byproducts of life as it goes about its metabolism. That is the way that I think we're going to first really learn about whether or not there is life on other worlds. Okay. All right. So we need special tools to do that. So are there any upcoming special tools? There are indeed. So as you heard from Renee, we, of course, are really excited about the launch of the James Webb Space Telescope. Now, this is an enormous investment. I'm not going to lie to you. It was expensive. It was $8 billion. $8 billion. And it will have a transformative impact across all fields of astrophysics. But what I think it will do is it will be the first observatory that can actually go and characterize the conditions on terrestrial planets, small rocky planets orbiting not the sun, but orbiting other stars. So James Webb, I think, will be at least as transformative to our understanding of the universe as the Hubble was in its time. And it is getting awfully close to a launch. The launch is supposed to be in 2018. The telescope is being assembled. It's being assembled at the NASA Goddard Space Flight Center. So that's just a little bit north of Washington, D.C. If you're ever in the area, go visit Goddard. I'm not sure you can see that telescope anymore. They're going to bundle it up and ship it soon to do some tests and ultimately on its way to the launch pad and then into space. But I like this picture because it really puts the size of the telescope to scale, right? So the Hubble, the main mirror of the Hubble was a little over 2 meters. So a little bit bigger than me, okay? So that would be like one of these individuals. But you can see how wide this telescope is. It's a much, much bigger telescope, and therefore it gathers a lot more light. It's much more powerful, allows us to see much more deeply into these planet atmospheres. So JDBC is going to be an important part of the story. The other important part of the story is a telescope that I spend a lot of my time thinking about, and that's something that we're trying to build on the ground. So just as JDubs T will be a much, much bigger and more powerful telescope than anything we've ever had in space, namely the Hubble, we want on the ground to build a telescope that's bigger and more powerful than anything we've had up until that point. And the telescope that I'm working very hard on is called the Giant Magellan Telescope. Okay, so this observatory, when it's constructed, will be much larger than any optical telescope ever built. Just to put it in perspective, that main collection of mirrors across the mirrors is about 25 meters. The very biggest telescopes, optical telescopes in existence right now, are 8 to 10 meters. Okay, so similarly, a much more powerful telescope allows us to see much more deeply. Okay, so of course, this is an artist rendering. What have we actually done for this telescope? Well, we are actually starting to build it. So this is an artist rendering of what those mirrors would look like drawn to scale with a person. So again, the James Webb, the thing we're putting in space, is smaller than one of these dishes. So this is a truly gigantic telescope. But we're building things, right? So this donut that everybody's sitting on, that's this central mirror. It's not polished yet, but we've just cast it under the football stadium at the University of Arizona. That's where there's enough space on the University of Arizona campus to actually build these giant mirrors and keep them. We've actually cast 4 of the mirrors, okay? And so ultimately we need 7. The telescope will be located in Chile, where there are truly amazing conditions. Very, very obviously, if you build an expensive telescope, you want to put it in a place where you can use it every single night. It will really allow us to do some pretty revolutionary studies, which I'll get back to in a moment. Okay, so with that in mind, we're building the Giant Magellan Telescope on the ground. We are almost ready to launch the James Webb Space Telescope. So maybe these telescopes will allow us to study the atmospheres of small rocky planets the way that the current telescopes that we have, the 8 and 10 meters on the ground, Hubble in space, have allowed us to study the atmospheres of gas giants, right? We've been doing that for about 10 years. So we're building the telescopes. What's the what's the hang up, right? So the hang up is we actually don't know where to point them. So we haven't actually found the planets, the Earth-like planets yet, that we're going to study. Okay, so that's the trick. So we are going to build these. The Giant Magellan Telescope we think will get on sky in around 2022. JDubs T will launch in about a year and a half. Okay, we need to hurry up and make sure we actually find the small rocky planets that pass in front of their stars, so we can actually go and point these telescopes at them when they're operational. So what's the challenge on that front? Here's the challenge. So this is reminding you of the scale of the problem. Okay, so there's a picture of the sun. You can see there's some sunspots, and then there's this thing. That's what the Earth would look like going in front of the sun to an alien astronomer. Okay, so the Earth is really, really small. And now you've got this guy standing in front of you from Harvard saying, we're not just interested in finding the planet, we want to study the atmosphere. Okay, so what that means is, imagine around this planet, there's this little onion skin of gas, and in that gas is this precious message, right? That's the gas that's saying, there's life here, there's oxygen, there's photosynthesis, there's methane, all the things that you associate with life, come and measure me. But it's this tiny little signal. He must be crazy to propose it. So why am I optimistic? Why am I bullish on this topic? Okay, so a very big factor has been the Kepler mission. So the Kepler mission launched in 2009. It had a 4-year mission. Then the second of the 4 reaction wheels, which basically allow us to point the telescope precisely in one part of the sky, failed. So we could no longer point the telescope exactly where we wanted to, so we had to change the mode in which we operate the observatory. Kepler is still running. We call it the K2 mission because it has a different way of operating, but it basically can no longer do the search for Earth-like planets the way that it had been doing for 4 years. Nonetheless, it is difficult to overstate the impact of the Kepler mission. The Kepler mission revolutionized our understanding of planets orbiting other stars by finding thousands of small planets, thousands of planets smaller than Neptune, many of them Earth-sized, and allowing us to really begin to probe their properties. So I'd like to show you just one example of those discoveries. So what does Kepler do? So what Kepler does is, here's the actual camera, there's the actual telescope, there's the launch, and what Kepler does is it looks at one patch of the sky for 4 years, and it looked at 150,000 stars. And all it did was measure the brightness of each of those stars every 30 minutes or so. So it just continually monitored the brightness. And most of the stars did absolutely nothing. Most of them are dead boring. They don't change in brightness. But every so often we find a star that does. So let me show you one of those. Okay, so here's an example of the Kepler data set. So we're measuring the brightness of the star, boom, 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 as a function of time. So these are days, so 200 days, 400 days, 600, so many years of data, several years of data. And then, of course, you see the scatter, this up and down. That's the noise. Each measurement is not perfect. So the light from the star bounces around. Then you see these gaps in the data, these white parts. That's when the telescope sometimes had to turn towards the Earth to downlink some data, so it couldn't gather. Sometimes the telescope suffered an anomaly and it went into what we call safe mode, which is basically like a fetal position until it can communicate with NASA and we bring it back. Okay? But that's not what I'm here to talk about. I'm here to talk about these little excursions. So then every so often, the star gets fainter. Okay, it dips down, it goes back up, it dips down, it goes back up. Those little blips, those are due to a planet that's passing around, and every time it goes in front of the star, it blocks a little bit of the starlight. It's a tiny, tiny change. Okay, there's many 9s here, so it's only blocking like a few parts in 10,000 of the starlight. But nonetheless, if you add all these up, so if you fold the data by that orbital period, then you get this signal. And that is a very, very clear detection of a planet. What's really neat, though, is much better than the human eye, computers are really good at folding up data and looking for little weak signals. And so after you remove this guy, if you do the same trick again and ask the computer, is there another planet in there? The computer says, yes, there is. You can't see it, but if I phase fold it, there it is. Okay? And that planet is only about the size of the Earth. That planet's only a titch bigger than the Earth. Okay, so a very clear detection. All of these points are fainter than the average of these points or these points, but something much, much more subtle, which you can't see in the unphased data. And Kepler did this thousands of times. Okay. So we can find planets that are the size of the Earth, but being the size of the Earth doesn't make you habitable. you also have to be the right temperature, right? So a habitable planet is, we think, a world that is a rocky planet with a thin ocean, and then the ocean has to be liquid. So it's not enough to be the right size and the right density, you also have to be the right temperature. And so we call that the habitable zone. So the idea is if you're too close to the star, then the water evaporates, so no oceans, obviously not very good. If you're too far from the star, the ocean freezes. But if you're in this kind of Goldilocks zone, then you might be a candidate to actually have life. A few years ago, a student working with me at Harvard named Courtney Dressen used the Kepler data and did a very careful analysis of the properties of the stars to be the first person in history to actually figure out how common Earth-like planets were in the galaxy. So she was the first person to ever know, she was, there coding it, she was the first person to get the answer. What fraction of stars have a planet that is both the same size and the same temperature? This was the topic of her PhD thesis. Pretty cool, right? So what's the answer? So, could it be 1 in a million? Could be that only one in a million stars has an Earth-like planet. If that's the case, then this idea of going and studying them is not going to work, because it means the closest example to us is still going to be so far away that it's not going to be realistic to study it with a telescope. But if the number is high, it means that maybe even the closest stars to us are going to host some of these planets. And indeed, that's what she found. So she found that the answer was 1 in 4. So 1 in 4 stars in the galaxy has a planet that is the same size and same temperature as the Earth. Okay. All right. So that makes my heart leap for joy, because now it means the targets are planet. Renee, your heart, I can see your heart leaping. Okay, so it means that there's a lot of targets. Okay. So so what about this idea now? We have the knowledge that around 1/4 of all the stars in the galaxy, there's a rocky planet the same size and same temperature as the Earth. Okay, so what's the challenge? Okay, the challenge is the actual stars that Kepler studied are not the ones we can study to look for oxygen and other biosignatures. The reason is Kepler looked at one patch of the sky, so the stars it studied were all very far away. That allowed us to do statistics, but they were not the closest stars. So we can't actually study the atmospheres of those planets. So what we need to do is we need to then follow up the Kepler mission with another project that will actually find the same population of planets, but around the very closest stars to us. So one of the challenges that we face in doing these studies is the distance to the star. Okay, we need that distance to be as small as possible. The farther I put a star from us, the fainter the star is to my telescope. I know my telescopes are going to be a certain size, so I can calculate out to what distance I can actually hope to study this atmosphere. The Kepler stars are too far away. Distance to the star is something we have to improve on. The other thing we have to improve on is the size of the star. Okay, so think about this. The planet goes in front of the star. If I want to make my job easier, is there any way I can shrink the star? If I can find planets orbiting small stars, then the planet and its atmosphere are large compared to the star, and I'm not as overwhelmed by the light of the central star. So those are the two things that we have to improve on to go from Kepler to actually having good targets to point JDBC T at. So with that in mind, a group of astronomers banded together and proposed the following mission to NASA called the Tess mission. So Tess is a small telescope. It's got 4 camera lenses. You can see them here, 1, 2, 3, 4. Each of those lenses is only about 10 centimeters in diameter. So those are if any of you do photography, these are basically telephoto lenses that are broadly comparable to things that you might use to take photos. These are more expensive because they have to be able to survive in space, but the basic optics are not that different. And so Tess is under construction, and Tess's goal is to survey all the stars in the sky to look for the population of planets that Kepler had found, but to find them closer to us. And so Tess is going to launch in December of 2017. Now, I think I can share with you one concern that we have with the Tess mission, which is you may have heard that there was an explosion at Cape Canaveral a few months ago. That was the SpaceX launch pad. We're planning to launch on a SpaceX Falcon 9 rocket. And so we don't yet know the extent of the damage to the launch pad. But this is the reality of going to space. It is tough. It is tough engineering. It is dangerous. And we hope that SpaceX will be able to get back to the capacity of launching, and we'll be able to get our satellite out on the time scale that we want. Keep in mind, we want to find these planets early. We want to launch in December 2017 because JDubs T is going up only about 10 months later. And we want to have planets to give to JDubs T so that it can study them. Okay, so Tess is very, very exciting part of the story. I think it's going to be a lot of fun. But what Tess won't do is do that second part of the problem. It's not going to shrink the stars. Tess is very sensitive to looking at stars like the sun, and nearby stars. But it's still we're going to be left with stars that are awfully big compared to their planets. So is there anything we can do to improve on that? So as it turns out, I was told a big lie, a big fat lie in high school, which is that the sun is an average star. Okay, so if you remember one thing from tonight, the sun is not an average star. The sun is much, much bigger and brighter and more massive than most stars in the galaxy. Most stars in the galaxy are these small stars, about 1/3 to 1/4 the size of the sun. We call these red dwarfs or M dwarfs. And they outnumber us 12 to 1. 12 to 1. Okay, so if I draw a bubble around the sun and I go out 30 light years, I go out 30 light years. So that's like the nearby neighborhood for astronomers. Okay, that's like trick-or-treating distance. Okay, I got you. So you go out to that distance and you count up all the stars. In that volume of space, there are 20 sun-like stars. 20 sun-like stars. In that same volume, interspersed between all those sun-like stars, there are 247 M dwarfs. 247 of these red dwarf stars. Okay, they fuse hydrogen. They live a long time. We now know that they make planets. So they seem to me as perfectly decent targets as sun-like stars, but they offer this one incredible advantage because the star is small. Now, when our little precious atmosphere goes in front of that star, I've made my job a lot easier because I'm not facing such an overwhelming contrast from the star. So there are several benefits to these small stars. One is that the habitable zone, right, that distance at which I have to put a planet so that it has just the right temperature for liquid water is now tucked in close. Okay, so if this is my sun-like star, and there's some range of distances in which I can put a planet where I know in Montreal you're not uncomfortable with that temperature, but generally life wants liquid water most of the time. And so around a sun-like star, whatever that distance is, for these M dwarfs, it's tucked in close. And that has several benefits. That means that instead of seeing one blip a year, instead of one transit a year, now these stars go around every 2 weeks. Okay, or these planets go around every 2 weeks. So every 2 weeks, if a planet's in the habitable zone, every 2 weeks it goes in front of its star. So there's many, many more opportunities to study the atmosphere. Okay, the other benefit is just a sheer numbers game, and that's what I already alluded to. So here I'm actually showing you all the stars within that volume of space. Okay, so if I count up all the stars going up to 30 light years, I see these sort of 20 G dwarfs, these 20 sun-like stars. There's a few more massive stars. We call them A stars and F stars. But here they are. Here they're actually all shown schematically, all the M dwarfs. Okay, and we know the names of all these stars. I mean, they're well characterized. We know their distances. We've been studying them for decades. They just haven't been very sexy until now. So okay, so the idea is we don't just want to study nearby stars. We want to study the small stars because it's an opportunity. It's just an opportunity to go and actually probe the atmosphere with the telescopes that we're building. So with that in mind, I went and said, okay, what would it take to go and actually survey a reasonable volume of these small stars to look for these precious planets? So we wanted to look at several thousand of these M dwarf stars, these red dwarf stars. And so with that in mind, we went out and we built the mirth project. Okay, so the idea is we call them M dwarfs. We're looking for Earths. So we call the project mirth, okay, because it makes us happy to do this. And it's been a lot of fun. So basically what we decided we need to do was we needed to build arrays of telescopes. The stars are close by, so they're pretty bright, so I don't need a really big telescope to discover the planet. But the stars are all over the sky, right? We're in this bubble of all the nearby stars, so I can't just point my telescope in one direction. Every time I point in one direction, I could look at one star. But I want to look at 3,000 stars. So I need to have a whole bunch of telescopes that can each frantically survey all the different stars as they rise and set each night. Also, I need to have observatories in both hemispheres, right? I want to have telescopes in the north so I can look at the stars in the northern hemisphere. As you know, here you can't see the stars in the deep parts of the southern hemisphere, so I have to have a separate set of telescopes in the southern hemisphere. And this is what the enclosure looks like. So it's a roll-off enclosure. In there, you can actually see them. There's one of them. You can actually see these 8 telescopes in there. And then here's the enclosure in basically an old, this is a building that was built quickly after the launch of Sputnik, actually. It's a very old building that we took over to do satellite tracking at our mountaintop in Arizona. So altogether, we have 16 of these telescopes. And that makes up the mirth project. So mirth, there's a nicer picture of the telescopes in Chile. Every night, the roof rolls off, and they start exploring all these nearby bright stars. And this is what they do. They sort of gather data. I like showing this because this is actually night 1 of our project. And so it shows that on the first night, we didn't discover something. But we did on the second night. So now that's not a planet. That's an eclipse. That's a star going in front of the star. So interesting, but not exactly what we're after. But that is, in fact, our second night of data and so on. Okay, so how does mirth work? So the idea behind mirth is we have a list of stars, and we need to look at each of the stars every 20 minutes. Because why? Because those planets that are going around every 2 weeks, that are in the habitable zone, they spend about an hour in front of the star. That's how long it takes for them to transit the star, and then we have to wait another 2 weeks until they come around again. So I don't want to miss that transit. So I can't look every few hours. I have to look every 20 minutes, so I'm not going to miss it. And they're going to look at all sorts of different stars. So I want to show you a movie of what that looks like in practice. So let me just bring down the lights a little bit here. There. All right, so this is going to be a time-lapse movie of mirth in operation on a very special night. And this telescope in the array is looking at a whole bunch of stars, and I'm plotting data from just one of those stars. So it takes a data point, boring, takes a data point, boring, there's another data. So it's just going about its business on its survey. And then all of a sudden it takes that data point, and it notices that that data point is fainter than these, and it switches in real time. It switched instantly what it was doing, and it simply stays on that one star until the star brightens up again, and then it goes back to its regular observing mode. Meanwhile, I'm sleeping, everybody's sleeping, we've got 4 kids at home, I get to be home with the family. That is the discovery of the first Earth-sized planet orbiting a nearby star. So what's really cool about that is, we wanted to talk to the press about this, and the press always asks, can you tell me about the moment of discovery? And normally you have to give this kind of painful explanation about how science is a slow process, and you had to build up your confidence in some signal over many years. But actually, in this case, I could just show them a movie and say, yeah, it was May 11th, 2015. Here's the exact moment on the telescope that did it. So we're very, very proud of that. So that's the first time. That's the first time that we have a planet that is the exact, it's almost the exact same size as the Earth, but now it goes in front of a very small star that's very nearby. And so now we can actually go and study this kind of world. Kepler found many such worlds like that, but none of them were accessible to us. All we would ever know about those worlds was their existence. Here now, nothing stops us. We can ask, does it have moons? What's its density? What are the, maybe even atmospheric constituents? Okay, so where do we go from here? So, JDubs T will be humanity's first opportunity to really probe the atmospheres of Earth-like planets. So JDubs T will have the capacity to parse the light from the star as it goes through the planetary atmosphere and ask what does it tell us about the planetary atmosphere. But I really want to point out that the trick with a telescope is a telescope isn't just the big mirror that gathers the light, right? When you use a telescope, there's another important part of that process, which is your eye, right? So it isn't enough to gather the light. You need an instrument, in your case, your eye and your brain, that tells you about the information contained within that light. JDubs T is not just a telescope. At the back of the telescope is not a human eye. We're not sending anybody out there, as far as I know. Renee? No, we're not. Okay. Grad students are all like, all right. So the instrument on the back of the telescope is something that has to be very carefully crafted. And of course, that's the Canadian contribution to the James Webb Space Telescope, is that instrument. Renee Doyon is the PI, and it's called mirth. And so this very impressive machine goes on the back of the telescope. It's one of 4 instruments on the telescope, and it will allow us to parse the light from the star and actually look for different chemical constituents in the atmosphere of the planet. And it is specifically designed, I think all the other instruments have more general purposes. This one is really motivated by the desire to study exoplanet atmospheres. And it is shipped. It has left the Canadian border. It is being integrated. Is this correct? It's being integrated into the telescope, and then they do all sorts of shaking tests to make sure that it can survive the stresses of launch, and that when it gets up, you know, JDubs T is going to be farther from the Earth than any human has ever been. There was no fixing James Webb the way we did with Hubble. So things cannot fail. So it'll survive those tests and then go out into space. Okay. All right, very good. So then on the ground, remember this is the other guy in the story, the Giant Magellan Telescope. So JDubs T will get there first. JDubs T will allow us to see what molecules are present in the atmosphere. Is there water? Is there carbon dioxide? Maybe even is there methane? JDubs T, however, will not, I think, do a great job looking at the most important gas to actually ask if there is life, which is oxygen. Okay, so JDubs T will tell us about the conditions on the planet, but just because of the wavelengths where it's sensitive, it might do it, but because of the wavelengths where it's sensitive and the amount of light can gather, I think it can't quite actually tell us about oxygen, which is the actual biosignature gas. Now, oxygen itself is not enough. You need these other gases to give context, to allow you to say this really is due to life and not just due to geological activity. But then the Giant Magellan Telescope, which will then get on the scene a few years later, I think really will allow us to look at oxygen. And just like the nearest instrument for JDubs T, what we're building at the Center for Astrophysics in Cambridge, Massachusetts, is a very special spectrograph. So this is an enormous instrument. Okay, that's 18 feet by 9 feet. I know you're in metric units, so that's 357 quatlus. It's big. I'm kidding. I'm Canadian. Come on. Anyway, the point is, it's a very, very big spectrograph that will very precisely parse the light from the star. And the trick is, you know, of course, so we get this big piece of glass. We're looking up through our atmosphere, trying to study another planet's atmosphere. What are we looking for? We're looking for oxygen. Well, you don't want to be fooled by oxygen. I mean, we're looking through oxygen to try to make that measurement. So what we have to do is spread the light out very carefully, and basically it's the fact that there's a Doppler shift of the Earth relative to that other planet that allows us to see the two signals seesaw back and forth against each other. So we can subtract the oxygen in our own atmosphere to actually see the oxygen if it's there in the exoplanet atmosphere. Okay, so that's why we need this very, very special instrument, which is called GClass, the GClass Spectrograph. So a very difficult undertaking. There's really never been an instrument built like it before on a very special telescope, the Giant Magellan Telescope, with its huge collection of mirrors. Nearest on JDubs T, GClass on the GMT, I think together the information for both instruments, I think if we did find such a planet that we could study, the one I showed you was a little too hot. We really do need a planet that is Earth-sized but a little bit cooler, but I think we're onto something. With some data recently gathered with mirth. If we can then apply both those telescopes to that kind of a planet, then I think together we might be able to conclude that, you know, if we do see oxygen and we see a bunch of other gases, that the only plausible explanation really is life. I think that, you know, I don't know if there will be such an unambiguous interpretation of the data. I think that detecting oxygen is my goal. Whether or not that allows us to conclude that there's life, or whether there'll be a debate about what the origin of that oxygen is, that's science at its best. That is something that we may debate for many years, and what I think we'll do is come up with tests that allow us to say, if it's due to geology, there should be something else we can measure. If it's due to life, there's something else we can measure that will distinguish between what is the provenance of that molecular oxygen. So with these new observatories, we, I think, really may make the first discovery of life on a planet other than the Earth. So not spaceships, not radio telescopes, but something that actually might come to pass on a timescale of 5 to 10 years. So this is not something for the next generation. This really is something that we may get to all be part of. And I want you to feel part of this. I don't, I want you to realize that this is something that I think all at some level can participate in. The impact of this will extend well beyond astronomy. So as astronomers, we're very lucky because it falls to us to make these discoveries because we have the tools. We know how to build the telescopes, how to operate them, how to analyze the data. But the impact of what we find, if we do find life on other planets, I think that that's something that extends well beyond astronomy. I think it'll engage life scientists. I think immediately there'll be questions about, is it DNA-based? Is there complex life, or is it just photosynthetic bacteria? Questions that I don't even know how we might answer those yet telescopically, but the things we're pursuing now are not things that were foreseen before we knew about transiting planets. We have these ideas as the opportunities unfold in front of us. So I really do think it will change, have an impact beyond just astronomy and even beyond science. I think it'll actually change how a lot of people view their kind of place in the cosmos. And that's sort of been what astronomy has always done at the best, right? Astronomy has told us that the duration of a human life is very, very short compared to the span of the universe, right? That's a crushing conclusion, but it really puts your life in perspective, that we are here for a brief moment in the universe's history. Astronomy has also told us that the scale, our scale, our physical size is tiny compared to the vastness of space. I think I think people view themselves differently when they understand that. I think similarly, knowing whether or not we are the only inhabited planet, that is possible, the only inhabited planet, could be, or that actually we're just one of many worlds hosting life, that similarly, I think you think of yourself differently if you know that you live in that universe. So I asked my students, we get some really great grad students at Harvard, and I asked them, what does this mean to you, these kind of giant telescopes that we're building? I told you, for me, they're like spaceships, right? So I asked these students, and I said, I'm going to go give a public talk. I want to end with your thoughts. And so one of my students, Hannah Diamond Lowe, who is just starting her second year at Harvard, wrote the following. And this is a picture of Hannah. She was down observing at Magellan. So these are some telescopes that Harvard's part of in Chile. There's 2 of them. And she sent me the following quote. So I wanted to share that with you. And she said, spending time at one of the biggest telescopes in the world has given me a grand perspective on the accomplishments of humanity. From this vantage point, detecting signs of extraterrestrial life seems well within our reach. I think it's fair to say like 10, 20 years ago, that was a great way to be thought of kind of a crazy person, to definitely not get tenure at Harvard. Here we have students coming to our university. They're passionate about this. They're going to do it. I really think that they, with the tools that we've all invested in as a nation, as a community, that they actually can go and aspire to make these discoveries. So I want to acknowledge the funding agencies that have paid for the work that I've showed you today. It would not be possible without them. And I do want to point out it's an interesting connection between federal funding and private funding. So we have benefited from funding from the National Science Foundation and from NASA, but also on the private side, the David and Lucille Packard Foundation, the John Templeton Foundation. They have each complemented each other by providing support for this work. Most importantly, of course, I'm not the one doing this, right? I try to bring together good people. I try to get them money. I try to talk with them about their ideas. But this work that I'm showing you has been by a team. I'm delighted to be part of that team. I'm going to tell you their names because I'm so proud of their work. Zach Berta-Thompson, Jason Dittman, Courtney Dressing, I mentioned. She was the student who had deduced the rate of occurrence. Jonathan Irwin, he's the guy that really makes mirth happen. He's a magician with telescopes and with data. Mercedes Lopez Morales, Elizabeth Newton, and Jennifer Winters. That's the team of top scientists at the Harvard Smithsonian Center for Astrophysics that are really making this happen. Okay, so what happens now? So you're going to go talk. So at breakfast tomorrow, you're going to talk to friends and family, talk to your kids. These are the things, this is what you're going to talk about at breakfast. Okay? So these are the takeaway points. The takeaway points are the following. First of all, red dwarfs are the most common star in the galaxy. Okay? So not sun-like stars. And there's at least one habitable planet for every 4 red dwarfs. It could actually be higher. It's at least 1 in 4. Okay. Once we find the closest transiting Earths, which I am quite confident we are on the cusp of doing, once we find those planets that are both the same size and same temperature as the Earth, we can study their atmospheres with the next generation of powerful telescopes. We've done the math. We should be able to make those measurements. And then finally, the search for atmospheric biosignatures such as oxygen, I think that that is humanity's first attempt to go and answer the great question of whether or not we are alone. Okay, so that's what I had to say, and I'd be delighted to answer any questions you might have.
Thank you, David. Before we go to questions, I just want to comment that I'm sure when you chose the acronym mirth, the M, I'm sure you meant mille for 1,000 in French. Okay, questions?
So we are talking about farming here. Questions with the JDubs T, are we most interested in, for example, asteroids and other objects? Because, I mean, as you heard, there are a lot of discussion about asteroid mining, and there are a lot of interest from the private sector.
Yes.
So it may also help in getting money from those companies.
Right. Okay, great. So the question is about, I'm just going to repeat it so everyone can hear. The question was, what about asteroids and asteroid mining? And would that help bring in industrial partners? So it is true that if you could go out and pick up an asteroid and bring it to the Earth, it is just full of precious metals. Currently, the trouble is that the cost of doing that greatly exceeds the value of the actual. So even if the moon was made of gold, we could not afford to bring that back. True, right? How much did Apollo cost? So there are people working on that problem, and there are private companies that are trying to get going to go and develop the infrastructure. It's a pretty different infrastructure. I think James Webb and the GMT, that these telescopes are on a different path than what you would want to build to go up to the closest asteroids and try to get sample returns. But there are definitely some companies that are trying to make that happen.
So we are not planning on observing those asteroids with this microscope?
Yeah, some folks may want to, no, that's right. There's one of the things that we were talking about at the meeting this week is there's a lot of interest in, you build this incredibly powerful observatory, but you actually look at your own solar system. And we're interested in the asteroids because they tell us about how the solar system formed. Those are basically the leftover building blocks. The asteroids in the Kuiper Belt tell us about how the solar system came to be. If they also inform plans to mine some of them, then so much the better.
So I have a question regarding the exoplanet transit. So you're assuming you might get something within the habitable zone and the same size. What if there is a runaway greenhouse effect and then the climate change is so severe that the entire planet within the habitable zone is warmed up and has a Venus-like atmosphere? Would you consider that? And second question is, are you also thinking about the Fermi paradox? If there is life and it used to exist, but then it ceased to exist because of some orange president they had to nuke the planet or whatever.
Yeah, it's funny for you. I have to go confront this. So okay, so yeah, so great questions. Okay, so the first question was, what if a planet looks broadly like the Earth in terms of its distance from the star and its size, but actually is more like Venus, right? Venus is not that different in size or the amount of energy it receives from the sun than the Earth. So I think that's a great question, and that's why we have to go study the atmosphere. So if we were to, I think if we find a planet that looks broadly Earth-like, we can't conclude that it has life on it. We go and make these measurements. If we did these experiments and the atmosphere is Venus-like, we could distinguish that. The atmosphere of Venus is basically 100 times, 90 times higher pressure, and it's made exclusively, almost exclusively of carbon dioxide, which has a very strong spectroscopic signal, something that'd be really easy to measure actually with the nearest instrument, as opposed to our atmosphere. So we can actually I think that what these studies will do is they will really push us deeper into thinking about what are the conditions under which planets maintain habitability. When do they have what you correctly called a runaway greenhouse effect? So if you get a little too close to the sun, some of the water starts migrating up into the upper atmosphere. Water itself is a really powerful greenhouse gas, and so then it's like an insulating blanket that just piles on. Then the question about the Fermi paradox. So the Fermi paradox is, where are they, right? You know, if there was a planet that formed life and resulted in intelligent civilization, even if that happened only a little bit earlier than us, cosmically speaking, there's been millions, billions of years. Surely if one such civilization had grown up, they could have colonized the whole galaxy on a timescale short compared to the age of the galaxy. So why don't we find spaceships on the moon, evidence that they've been here? And I think that that's an important intellectual contribution. I think that that's a very human, this idea that the natural consequence of life is to want to build spaceships and colonize the galaxy. Maybe just humans want to do that. I think that there's lots of life on the Earth that is not interested in that kind of activity. Maybe life on other planets, So it may be that there's lots of organisms out there that just are not interested in that particular outcome. So. And also, it may actually tell us that space travel is actually inherently really difficult. So.
Here.
Okay, I was wondering, have you considered that perhaps Northwest find something similar or Earth-like, that we're sort of ignoring the possibilities that alien life could have a different biology than we do? So maybe looking for oxygen is not what we should be doing. Maybe looking for another, gas or something like have water with the nitrogen, or I don't know. The fact that maybe alien life just doesn't look like us.
Right.
Functional.
Great question. So why, are we being too myopic? Are we being too narrow, looking for life as we know it? Couldn't life have some different chemistry that doesn't produce oxygen? Absolutely. I am proposing to do an experiment that I know how to interpret the answer. So I admit that what I'm proposing is narrow-minded and myopic. I am looking for life. I think there's a reason to think that if life forms on a planet, the one readily available energy source is the light from the star, the same thing that keeps the water liquid, and that life would want to interact, and that oxygen is the most abundant and the natural way to manipulate electrons and control that energy. So I think there's some reasons to think photosynthesis and oxygen are robust. But even setting that aside, I absolutely admit there could be planets with life on them that we study by this method. We don't see oxygen, and we just have to put our hands up and say, I don't know if there's life, but there's not life as we know it. I hope that some students that I work with have great ideas about how to come up with an experiment that would conclusively allow us to interpret that data. And I think you're absolutely right. So we just are going to begin by asking questions that we know how to understand the answer, and that is basically looking for life as we know it. Yeah.
Two more questions. Here.
My question is about the transit method. In the graph of the intensity and variation of the star of the Kepler method, how can you make sure that the variation of the intensity is not nice? It is a plan, but it's not nice because like effect or another astro.
Right. So great question. So when we look at that Kepler data, how can we be sure that that's due to a planet and not due to some other effect? So we know it's not noise in the sense of just random stochastic noise, because it is precisely periodic. It's always the same depth. But then the idea is you have other models in your head about what that could be. So could it be a sunspot? So a sunspot doesn't work because a sunspot is visible half the time, right? It's visible, then not visible. These transits, they're only for short blips of time. So that's consistent with Keplerian orbital motion, but not with the sunspot. And then the real trick is to go, what we spend most of our time doing with Kepler is validating the planets, just showing they really are that those signals are due to planets. If we go and get the Doppler measurements, and exactly as we expect from the transit, the photometry data, we can see the star go back and forth as it's being tugged by some gravitational object. And then we calculate the density, and it's consistent with planetary composition. That I think. So the point is, there are many teams of astronomers that try to disprove each other's planets. And occasionally they succeed, but most of the time they confirm the findings. So it's, I think it's a bit of the kind of slightly competitive atmosphere of research science that actually serves us very well in that case.
Okay, in the back.
My question is more related to the criteria that you apply when you're looking at this data set for all the 2,000 exoplanets. So one thing you mentioned is that you're clearly interested in finding out the atmosphere. What are the other criteria which would also help you identify whether the planet could be habitable versus non-habitable? For example, the orbit consideration, whether it's uniform or non-uniform or it's elliptical, maybe that could make the atmosphere sort of finicky and not really habitable for life. And so do you have that sort of data for all the exoplanets?
Great question. You spoke very clearly, so I'm not sure I have to repeat it, but to some, I think that you're exactly right. What other information do we have, in addition to just the size and the average temperature, that really make us think it might be habitable or not? And we do have some information, and there's other information that we don't have that we are trying to come up with ways how to measure. So you mentioned the ellipticity. That's right. So we would like to know whether the planet's in a circular orbit, like the Earth is almost circular, to within 2% it's circular, so that as it goes around the sun, it doesn't change very much in temperature. That's not true for Mars, right? Mars is quite elliptical. Mars, the reason for seasons on Mars is the wrong reason that people write on Tess at McGill University and at Harvard and so on, which is they think it has to do with distance from the star, right? That's actually true in the case of Mars. And if you had a very elliptical orbit, it would be a terrible place for life because your oceans would freeze and evaporate all the time. There are some real concerns about these M dwarfs that astronomers have. So one is that the M dwarfs, these stars put out a lot of ultraviolet radiation. So maybe that's a good thing for life. I don't know. Maybe it promotes, evolution and mutation and so on. But it definitely is hazardous to the atmosphere. A lot of ultraviolet radiation can remove the atmosphere of a young planet. And obviously, once the planet loses the atmosphere, if it doesn't have another way to produce an atmosphere, it would be a pretty inhospitable place for life. The other is the planets are tucked in very close to their stars. And because they're in so close to their stars, they become tidally locked, the way that the moon always shows us the same face. These planets would always have one part of the planet that was in constant daylight and one part that was in constant darkness. And the thinking was that that might be bad for life because the atmosphere would eventually freeze out on the cold night side. More sophisticated calculations show that that's unlikely to be a worry because provided there's oceans and atmosphere, it'll redistribute the energy. Just, it'd be equivalent to saying, well, gosh, after the sun sets in Montreal, doesn't it go to absolute 0 Kelvin, right? No, there's some inertia in the system, thank God. And so, it's a little bit colder, but it's still hospitable. So, those things are not accessible to us. We think that they're tidally locked, but we actually can't yet measure that directly. And there are many, many different criteria that we do think about. And the last one I'll just measure is geologic activity. So we think that an essential part of life on the Earth is that we have active plate tectonics, which allows cycling of material between the atmosphere and between the mantle. That's the way the Earth actually, before humans got involved, the way the Earth controlled its temperature. It controlled the amount of carbon in the atmosphere through this method. If a planet has solidified and no longer has that, we think that it would have this runaway greenhouse effect. It would ultimately become inhospitable. And that's something we could hope to measure maybe through studying whether it has active magnetic fields. So it's a great question. That's a whole field of science, thinking about those things.
Okay, I think we can go on for quite a long time, so I suggest we stop here. But don't go away. We have some gifts to give you. In fact, we have one first for David. So this is a modest present to remind you of our place here. So, well, how about you drink that generous? Okay. We have some gifts to you, so Kelly is going to do that.
Okay, so I'm going to try to be as loud as possible. Thank you, everyone, for coming out. So raise your hand if this is your very first Astro Night. Wow, right? Okay, so if this is your first Astro Night and you would like to hear more about Astro Night, please like us on Facebook, follow us on Twitter. We have a bunch of previous Astro Night talks which we have recorded and they're up on YouTube. So you can watch those as well. And now I am going to do the drawing for this lovely McGill Space Institute mug, which is the best thing we're giving away tonight. Okay. I hope you have good handwriting. Okay. This is Dan Claudio Sherlarue. Woo! Okay, come down and get your prize.
Okay, so just stay 1 minute. I'll try to speak loud as well, but I have no voice, as you can see. So as you might know, this event was organized conjointly between Astro Night by MSI. It was also organized by the Canadian Space Agency. Thanks to them for their organization. And it was also organized by iREx, which is the Institute for Research on Exoplanets. We are based in Montreal, and we have researchers from McGill and Université de Montréal, which you already heard me saying that if you participate in our contest. So today I'm going to draw 3 winners. And if you win, I will contact you so you can choose between the 4 amazing prizes that were available. So among them, there's a beautiful book in French by Hubert Reeves that is very well illustrated. You could also choose membership to Québec Science. There's a very good book in English about astronomy. And there's also the possibility to win the TV series Cosmos, which is awesome. So maybe I will ask René to draw the first winner. And maybe I will ask David to draw the second winner. Okay. And Lee. So the first winner is Robert Goma. Congratulations. The second winner is Charles Lagacé. Congratulations. And you can come to me if you want. And the last winner is Christophe Munden. Sorry if I don't pronounce this right. Congratulations. Have a nice evening, everyone. Thanks for coming.